So today we'll be talking about these small things, about chips and embedded development. So first of all, let me do a small introduction here where I came from. I came from Brno, more than 1,000 kilometers away. And you may be asking why the city is interesting. For example, there were this guy in the city, Johann Gregor Mendel, the inventor of scientific genetics. Yeah? There were even this guy, Kurt Gödel, who is very important in computer science, his work. Yeah, definitely. And also Victor Kaplan, the guy who invented the Kaplan turbine, which is installed also in this country somewhere, and making electricity. And also, you may know this guy who is Adam Ondra and he's living in Brno also. So he's the climber who set the hardest route in the world, hardest climbing route. And also, Brno happens to be a home of European branch of Espressif systems. The company is located in China, India, Brazil, Singapore, and in Europe. And we had already some conversation with people and were asking, hey, what you are doing? What are you producing? So at our website, you can find several boards and dev kits that people can use to build their home automation or their projects. So we are basically manufacturing those small chips, these dev kits. This is just a wrapper around the thing that makes easier for developers to work on it. So we have even like this fancy S3 box, and we are trying to do things open source. And I believe that this is a good thing also in the Swift world, like the Swift language itself is open source. And this is really nice because we can even do the open hardware stuff. So we can do not only open software, but open hardware. So we publish everything. So if you are interested, you can like grab the files from the internet and print it, 3D print some stuff, or send it to manufacturer. You may be aware that there is another company which is part of Espressif, and it's the M5 stack. They are doing this fancy stuff with our chips. So the small chip that is driving the drone is ESP32, and the controller with the joystick is also ESP32. Okay, so that's the hardware part. Now let me show you this part of talk that was during WWDC 2024, where Jakub Mraček actually introduced the embedded Swift, Go Small with embedded Swift. And I was watching this talk and like, hey, that's really cool what they did in that talk, because they were able to blink LED. You may say, okay, why this is interesting. Blinking LED in embedded world, it's like hello world in like normal programming. So if you are able to blink LED, you proved that you got working embedded hardware. But not only that, they were able to connect it to Matter and connect it to Apple HomeKit and control these LED colors and everything. I said, oh, that's really interesting. I was doing a lot of work with Rust before. We were making Rust possible, even the bare metal Rust on ESPs. And it took us quite a long time to do what these guys from the Swift compiler team showed. And I was like, hey, this is really cool what they are doing. So I went through the steps that Kuba was presenting here, and I wrote this article that actually was the reason why I was invited here. And I walk through the step and describe basically what they need and what they built. So basically they are using ESP32C6, like this board. I have some of those boards at the booth. And then they are using ESP-IDF. Normally, if you program for iOS or macOS, you got Xcode, and then you got all the header files and all the stuff required to build for the operating system. This is similar thing, just ESP-IDF is operating system for these small things. because you are not able to fit iOS here, unfortunately, or BSD. Some people tried Linux there, but it took like 1 minute to boot, and yeah, with light bulb, you do not want to turn it on and then wait for 1 minute till it turns on. So yeah, so there are specialized operating systems like ESP-IDF, which is using FreeRTOS. There are others like Zephyr, which is like very popular in industry and automotive, where also Swift is possible. In this case, we will use this ESP-IDF. For you, it means that you can include some bridging headers, and suddenly, magically, you got all the functionality available. And then we will go with latest, greatest Swift 6 nightly toolchain. So if you like to play with this, you have to install nightly because all the cool features are there, and it's evolving like really fast, and new methods and new stuff is being added to that project. So it's very active, this development. So you can download macOS or Linux toolchain and play with it. I already made some recording here in AskInema how the build looks like. So this will pull you a little bit out from your cozy environment of Xcode into the command line, but just to get an idea. So you clone the project from the Git, and then you make this export toolchain, and then you are able to build a project. So you may see that I'm typing there some commands like idfpy something, idfpy build, and then flash and monitor. So basically, this is the workflow of embedded development. It's slightly different than like normal development for iOS, where you just run it. Basically, in iOS, there is like uploading the application to the phone or to the simulator. With embedded hardware, you need to flash it, and it takes some time. The bigger the firmware, the longer the time. So if you are uploading 1 megabyte, it might take you up to a minute, or if you are uploading to 5 megabytes, it might take you 4 minutes. So you have to be careful how big the firmware is. So this is how it works. Let me mention here the important environment variable that you should use. So if you'd like to use this toolchain, please make sure that you call this magical bundler row command, that you will set up this toolchain variable properly, and then you are able to use this toolchain during the compilation. One important thing for the embedded development is so-called target. Target is basically the, let's say, name of the chip, because we are manufacturing multiple of them. This is called C6. It has Wi-Fi 6 support, Thread, Zigbee, and so on. But there are chips like old ESP32, which has Wi-Fi, but doesn't have Thread support. So you have to choose which chip you use for the flashing. This is so-called set target, and then you can call build flash monitor, and it will upload the stuff there. So, okay, that's just like, okay, there are some steps that you need to do. It's not only for like our chips, but also for any other embedded chips. There is similar workflow. So let me show you some code, and this is like pretty simple. Let's zoom in. So how the embedded Swift look like? There is a main, or in this case, up main. This is the main entry point for embedded application, nothing special. You call print, and you can print a string. That's nice. And this is the example that is controlling LED strips. So you can see that there is so-called GPIO, this small pin here. You can see, or you can't because it's too small. It's so-called GPIO, and it has number, and you can tell MCU to control this GPIO, so you can turn it on, off, you can set voltage which should be sent to the pin, and this way you can control it. So I think that it's relatively simple. Swift code, you got the infinite loop. There is some looping through the pixels, and then you call refresh, and with that the thing is working. So With normal development for iOS, you have the iOS simulator, and the similar thing we have for embedded development. We partnered with Walkwi, and we created this kind of simulator that is able to simulate all of our chips. So let me show you how the LED blinking looks like. I just run it in, and it's blinking. Okay. But what you can see in the simulator is a whole bootlog, a lot of stuff that makes sense to embedded developers. For us, it's important hello from Swift on ESP32C6. So you can see that I am showing you from the web browser, but we have the integration also with IDEs. So you can, let me stop the simulation and let me try to show other IDEs. For example, JetBrains, this is Rust Rover, but it works with CLion or other IDEs from JetBrains, and you can actually do the simulation inside the IDE too. So that's one thing. Okay, and you can use also VS Code to do the similar thing and run the simulation. Basically, in the VS Code, it's sufficient to open the diagram JSON and run the simulation. So, and let me show you also the other example that was there. For example, this is the LED strips. We are able to simulate even multiple NeoPixel LEDs. This is basically you are sending an array of colors, and it's changing the color. Unfortunately, the color is not that visible since the gamma is low. But yeah, you can have a feeling that, okay, there's something happening. Okay. So let's look at what is this embedded Swift. It's kind of interesting because it's a subset of Swift. So it's not a dialect, it's not a special language, it's not a fork of the language, but it's a subset. You have all the good things there, like generics, protocols, tuples, enums, options, and so on. So all the classical stuff. But you don't have like runtime reflection or meta types, or even any is not present there. But you can use generics in most of cases relatively easily. So not all the software written in Swift is possible to compile for embedded Swift. But you can adopt it. And it will also, once it's written in this way, it can also run in Apple's Secure Enclave. Okay, so let's look at those Swift embedded examples. That is under github.com/Apple Swift embedded examples. You can see that there are multiple hardwares present. For example, there is even the Raspberry Pi, and for us, the most interesting is ESP32. Here is the LED strip that I was showing before, and blinking LED. So how does the embedded project look like? So let's go for Blinky first. As you can see, there are just few files. There is a CMake list, because this is CMake-based project. You do not need to worry about this stuff. IDF-Py command and the build system is taking care of it. So you just need to have this file present at the project. So there is this CMake list, and the main application is here in this directory. And you may see, okay, here is the main Swift. That's the code that I showed you before, or relatively similar one. That is doing some infinite loop and blinking LED. So yeah, this we can understand, it's no problem. Let's look at how the LED is implemented. So there is a struct, and it has init. We can tell this LED on which GPIO it's living. So I can say GPIO 0, 12, or something like that, and then I can set a value to true or false, and it will be translated then into the blinking LED. So, and how is the integration with underlying layers done? This is a very good thing about Swift, that Swift already is able to talk to the C libraries thanks to Objective-C, and has this nice thing about the bridging headers. So basically, you just include some headers from ESP-IDF. You can see the FreeRTOS. By the way, do you know how many files has the FreeRTOS kernel? Any guess? I would say it's 100. No one. So actually, it's 7 files. So it's a very small kernel, that's the reason why it's running on embedded devices. So this way, you import it, and you can use all the goodness of the Swift about this layer. Let me mention also some more complex CMakes. You just need to copy it. Basically, here you register your Swift files like main and LED Swift. This is the magic that you just need to copy. It's some compiler flags that you need to pass to the compiler to make all the stuff happen. We are now trying to work with Swift team how to reduce these compiler flags, so you probably in the future won't need this magic. Right now, just copy it there, and it will be fine. So that's how this project looked like. Okay, let's look at the strip. So now we learned how this project is. So in the main directory, we have this again main file, which contains the main code. It looks pretty high level. Nothing special. Here is the implementation logic for struct let strip. Strip is the set of NeoPixel LEDs. Hello. And here you can set the colors and other stuff. If you are into the home automation, another repo that you can find on the GitHub is Swift Matter examples. Here is explained how you can use your HomeKit to blink with LED, blink with smart LED, and so on. So since our chips support Matter, you can connect it with whatever Apple ecosystem is there, and you can have working application there. So what I would like to show you next is, okay, so I tried to take it a little bit further. And here is the example that I wrote. It's about integrating graphical library SDL3. Anybody from gaming? Yeah, some game developers. Yeah, good. So you probably know the SDL library. It's open source library for handling graphics in multi-platform way. So you can have these graphics on Mac, Linux, Windows, Android, whatever. And it works, and it's like very easy to transport it. So I say, okay, let's see whether we are able to write a graphical application that is running on Swift and then make it happen. So it happens that, yeah, we are able to do it. So this is some screenshot from the simulation and how it looks like. So if you'd like to bring any third-party library like this SDL, this is an example. There might be other like LVGL or anything else. You need to register it in so-called IDF component YAML. Basically, all ESP-IDF projects are composed of component. Normally, the main is one component, but you can drag any other dependency. We call it in ESP-IDF as a component. So you can see that there is, for example, a component like LilFS. It's a file system that you can store your graphical assets on and flash it directly onto the device. And you can see that I imported, like, this is the C library. And thanks to the bridging header, I'm able to call it relatively easily. So you register it like this. Then in the bridging header, you mention all necessary includes from the C library. And then in the main application, you can use it. So let me show you the SDL init. Yeah, here. Yeah, so like in good old C, you can call SDL init and it will initialize the library, same like on desktop, you can do it here, and then initialize the application. So, I have the working demo there. It has a pretty nice frame rate. And this is another example how you can bring the C application or C libraries into the Swift ecosystem. So this is like very, very good. Another good thing about ESP-IDF is that you are able to use even pthreads. So if you need some support that requires multi-threading, not only task but multi-threading, it's supported here. Another thing that you can find in these examples is the GitHub workflows. I try to build these examples in that way that you have the end-to-end workflow. In desktop development or iOS development, it's often common that you have CI/CD. But in embedded development, it's not that often. It's kind of like 20 years ago. If you go to embedded development, suddenly, yeah, people are building the stuff or even the production stuff on their computer. And if this computer dies, then like, oh, we are doomed and we don't have the thing ready. The issue is that the installation of some tool chains for some vendors is so complex that it can take you one day just to set up the computer. In a good case, in a bad case, it's more than a week to install it. So it's not that easy like installing Xcode. It's way harder. So I try to put also this GitHub action example that build the application. So you can see that it's a little bit more elaborated. We are using some container with the ESP-IDF CI action. This basically pulls the container which contains the Linux image of the toolchain that I'm using. And then it's pulling also the embedded Swift. This is the Ubuntu version. Pulling it there, extracting it, integrating it. You can see like the export path. And then calling the IDF pipe build. So by this, you are able to build in CI ESP-IDF application, and we are able to do the tests. So I showed you the walkway before, and thanks to the walkway, we are able to use the walkway CI action. And the thing is that, again, in embedded development, it's not very common to have CI tests. It's like kind of luxury. Because if you would like to do CI on this thing, you will probably need a whole test bed with these chips. And setup of such a test bed is relatively complex. So as an alternative, it's possible to run this walkway simulator. It has also the command line mode. You basically pass that there a binary, which was built for the chip. It will boot, and then you can check for some, I don't know, rebooting, or if the chip is rebooting and it's not working, it's a sign that the firmware is broken. So let me show you how it looks like in the actions. So just to see how many build lines it produced. So now I'm building for 3 different hardware targets, P4, C3, C6. So there are all those different chip types. And let me show you the C6, and just to get an image how big the build is. So this is building, installing Swift, and now here runs the build of the application itself, and you can see many lines. Actually, the build itself is about like 1,700 files. It's pretty big. It can be make smaller, but this is just the like common standard that you will see normally. But with the GitHub action, it's pretty fast because you can parallelize, and for each target you can make different runner. So and let's check how the tests are looking in case of embedded development. Okay, so we have this embedded test with the walkway. Yeah, and there's some installation. Run CLI test. Yeah, you see the log from the chip that normally is booting. a lot of stuff, some calibration error, and here is the application with Swift entering the main loop and then test passed. So you can check this demo, ESP-SDL3 examples, and it contains everything, including the CI. Okay, so I was playing a little bit more with it because the original examples from Apple was just calling our C libraries, but they were not doing too much with connectivity. So I would like to build something that is doing something more, that you have a chip and then you connect a display to it, so we can display some weather, like it's snowing and it's 12 degrees Celsius plus, like on this screen. And it was not that completely easy, and I would like to show you which parts are a little bit more complex in embedded Swift if you'd like to write an application. So let's go and let's see this bigger application. So you can see that already there are more files. I introduced the wrapper C because some functions actually was necessary to have some wrapper function, because if you are calling C and it's a C function, it's no problem with Swift. But if it's a macro, you need to expand the macro before you call it. So for these cases, it's necessary to have wrapper functions. Yeah, we can live with it. There are some small wrappers, nothing like big fancy, but it's included in the project. Let's go to the main Swift, and you can see that already it has 667 lines, and it's a little bit bigger because to get the Wi-Fi running, actually, without the operating system, you need to do a little bit more dense and set it up. So basically, you can see that I have here the weather data struct, which is coming from open weather data. And I'm parsing the JSON there. And there's a lot of stuff happening. So let me find, here is the Wi-Fi in it. As you can see, it's relatively simple. We are able to do even a time sync, so we are able to call NTP servers, and we are able to fetch the weather data. So it looks like this, fetch the weather data from open weather. And we are, as you can see, we need to implement some HTTP GET method and react on it. So you can see that this is a C code. I didn't have time to rewrite it to more Swifty way. So this is kind of leaking from the embedded C world. But you can see that there are some like strange stuff, like here. And you might guess where the problem is rooted. So for example, string interpolation is not that great with embedded Swift. You are not able to interpolate string in so convenient way, like in Swift. And it's kind of limited. So let me show you the limitation. And scroll a little bit. Yeah, here it is. Here it's visible that for example, if I would like to create a sunrise and string, I have to do this it this way, like sunrise hour, sunrise minute, and so on. Other than that, there was not much other difficulties. So the string interpolation is kind of problematic in embedded Swift, but the guys are working on that. So maybe in future versions it will be even simpler than this my example here. So and let's run the simulation here. Yeah. So here are some data. Yeah. Okay. It's Stormy 22. Somewhere this is generated. And here is another good feature about the walkway. When you pause the simulation, it gives you the state of GPIOs, so you can see which part is configured properly and which is not. So you can see that, for example, here is the SPI2. SPI is bus for connecting displays. You can see that these pins are not used, so they are in so-called floating state. Here you can see UART. This is a serial console monitor. And with this, you can see what is basically happening on the chip, because if you just like run it on the physical chip, you're not able to tell, hey, this is SPI or not. You need to look into datasheet. It's super cool about the simulation here. So, about how to start developing for this embedded development. Many people are familiar with Arduino, so we recommend it as a kind of good starter because there are tons of examples written in Arduino, and you can use this Walkwick.com online simulator. You can choose a board that you want with the target, like S2, S3. You can choose even the more fancier, like S3 box, or recently Xiao devices from Seed Studio were added. And you can click on it, and online you can play with it. So this is how the code looks like in Arduino. You can run it and run the simulation and blink, blink, blink. This example is even better. It's blinking 3 LEDs, not 1. So definitely, if you like to start to play with it, you can go online, play with Walkwick. Once you know what the embedded development look like, you can start working with a real hardware. So there are even like this fancy Core S3 box from M5 Stack that can run the simulation. So, okay. One thing that I would like to mention here is another term that is used in the development. Often, if you like to work with graphics, it's so-called board support packages, or BSP. Because normally, if you connect display or any peripheral to the chip, you need to configure, hey, this pin is connected to MISO, this is to MOSI, this is SPI2, it's connected this way. And it's relatively hard work. If you don't have the data sheet, it's pretty impossible to like write your configuration properly. So that's the reason why we published so-called ESP-BSP. You can just include it in your project and it will get auto-configured. It's like simplifying the work. So if you go to GitHub, Espressif ESP-BSP, you can find there many boards that are already supported by the BSP. So it means that whatever hardware, oh, we went blank. Now it's blinking. Okay, better. So there are multiple boards that are already supported. So whichever board you choose and you write your application for the board, it's possible to switch the BSP and have different board selected, like the S3 box or even this rotary knob. Oh, this is very nice. It's like pre-configured for you. Okay. Then. One thing that we introduced also is this component registry. So if you are searching for some component that is doing specific logic, you do not need to port everything from the scratch again. I don't know, you have some library that is open source and you would like to bring it into the project. You can search the component registry, and it's very likely that somebody already ported it to the component registry. Even the board support packages are there. I published the SDL here. So if you happen to have a code that is using SDL, you can basically grab this component and use it. Yeah, so there are already some existing things. Or if you have sensors or hardware that is working with the board and you'd like to, I don't know, read some data from it, I don't know, temperature measurement, it's very likely that the driver already exists. So you can just use this existing component, put it into IDF YAML. Okay. Next thing that I like to mention here is this address, product.espressif.com. It's not that I'm trying to do the marketing, but I'm trying to like explain you how to select the proper chip, because it's kind of problematic, because we have like so many of them already that it's pretty hard for people to find out, hey, what makes sense for my project. You can see that, or you can't, I will zoom it in. There is like the P4, C6, S3, ESP32, or even legendary 8266. We are still manufacturing it, but you are not able to get Swift running there. For Swift, you need newer chips that are using RISC-V architecture. That's basically P4, H2, all the C chips. There are newer. It's like before we were using Extensa architecture for ESP32 and S3. It's like in Apple world, Apple was using Intel, and then they switched to their own chips like the M1 and M4, which they designed. And in our case, we are not using ARM as architecture, but RISC-V. And it allows us to use the upstream compilers. So Swift is running on all RISC-V targets. If you like the Extensa, you can join the discussion. There is a problem with LLVM patches. There are some pending patches. After they get merged, we can get even like ESP32 supported natively with Swift. So let's say that I would select here the C6. Zoom out a little bit. And here I can find which chips are available, like the C6. Here you see the block diagram, what is inside the chip, what it supports. Basically, it's like small PC, because it contains all the buses and everything on such a small chip. So, and here you can find more details. First thing that you will hit with Swift if you start working on it is that you have like insanely small amount of memory. So you have like 500 Ks of memory, and that's it. If you turn on Wi-Fi, you will lose another 100 K. So you have to be very careful about the memory, and in most cases, if application is crashing, it's because it's run out of memory. But with Swift, it can be handled relatively easily, and it can be monitored how much memory is left. Just to like warn you that, okay, this embedded development, the stuff is smaller. Even the frequencies are smaller. Here we are operating on 160 megahertz. You can even clock down the chip, and this is very useful if you'd like to save the power. So if you go to 80 megahertz, you will burn less energy than if you are operating in 160. You may ask why this is important. Because there are battery-operated solutions, and if you run your MCU at maximal speed, you will burn it in a day. One battery won't last too much, and yeah, that's not good. You can go even lower, below 80 megahertz, but then the Wi-Fi is not working. We are also having there multiple cores and so-called low-power MCU, another RISC-V core, that you can run and talk to the low-power devices. So, and the last thing here is if you'd like to compare some chips side by side, there is this product comparison, and you can select, I don't know, let's take Extensa S2 and C3, and you can see side by side where's the differences. Typical is the SRAM, that there is different amount of memories. For example, if you are creating a light bulb, you probably do not need that much memory. But if you are creating something with display, then you need memory for fonts, for rendering buffer, and so on. So in that case, it's good to have some extra memory. So that's another thing that you can find here. Good. Okay, so it already went dark. Some connection is not working properly and blinking. Yeah, we have blink. here. Okay. So I see that we are running out of time. Should you have any questions, I'll be here outside. I also prepare small giveaway for you. So if you'd like to win small C6 for you to try development of embedded hardware, there is a small challenge. So you can try to solve this challenge at the booth in front of the auditorium and win this P4, C6, or we have even special giveaway for the P4. This is the super new board that is under development. And you may see that I'm running there even like application on really big display with a touch screen. So that will be available there. Okay, so that's probably it about the embedded development. So I showed you how the development look like, what tools do you need, and what are some limitations, and how to find a chip for your project. I invite you to join also Swift org, and there is a discussion forum for embedded Swift. So if you are interested, you can join the forum and seek for the embedded topics and get some involvement there. If you have some opinions how something should be written or created in embedded Swift, you're more than welcome to discuss it there. Yeah. So.
Is there anybody for a question? We have time for like 1 or 2 questions. Nobody? Oh, in the back over there and in the front over here. Ah!
No, it's there. The question ran down.
I think you tried to hit Marco, right?
Hello. Thanks for a really interesting talk. Not typical for, I think, any iOS event. So yeah, my question is, I've seen there the process of communicating with the server via API, and there was a kind of HTTP client. Is it provided by some foundation libraries inside operating system, or we also should maybe download other libraries or write ourselves?
Okay, thank you very much for the question. So regarding this particular example, it's using HTTP client from ESP-IDF, but there could be others. So I use this because I know that it works with ESP-IDF. But you can write your own. There can be like different implementations. So this is just one of examples. We know that there are several other implementation of HTTP or HTTPS. For example, in case of HTTPS, there is also Valve SSL. They have their own implementation that is more optimal for some use cases. So it depends. ESP-IDF provides by default some components, and you may decide to use it or to use something else that suits you more and is more closer to your use case. I have to mention that this is relatively early with Swift embedded. There are a lot of changes. In the forum you may find already that there is some other better HTTP client.
And there's one final question over there, the gentleman in the black jacket.
Hi. I basically have 2 questions, but they're related to each other. The first one is, are there any kind of differences in performance when using Swift in the embedded systems compared to other languages? Like, as I know, C and assembly are quite popular in here. That's the first one. The second one is, as I noticed, Swift is kind of new in embedded systems based on the GitHub repository. And just your opinion, do you think it will be backed very heavily in the future? What will be the future of Swift in the embedded systems?
Okay, so thank you very much for those questions. So regarding the performance, it's very close to C or to Rust because it's basically using the LLVM. We already have some Rust development and it has good performance. It's using the same LLVM that is compiling the Rust part, so it's relatively good. If we compare the performance, the worst performance that you might get on MCUs is using some interpreted language, like for example Python. There are a lot of projects with MicroPython, which is like super okay. And we even see that there are startups who started with other languages like this MicroPython, and then they switched to some native implementation, and it could be even like Swift. So it's in case of Swift, it's basically LLVM backend is producing the binary, and it's linked together with the C code, so it's like very nice and very high. So that was the first question. And could you remind me about the second?
Yeah, since Swift in embedded system is relatively new,
Yeah,
so I'm just curious if it will be backed heavily. Like, what's your opinion?
My opinion is that there will be support because it really makes sense, since these prototypes, it makes it easier for developers to write for embedded hardware. Before, you have the only option to write it in C or probably in Rust, and that's it. But both are like pretty hard to learn and pretty cumbersome in some cases. So there is definitely the value, and there is ongoing discussion, and we see also some contributions that are happening to the Swift embedded recently, and it seems that it's getting some attention. So I'm not able to tell from the Apple perspective what they think about, but it seems they are invested into this.